So, all right. So for chapter 5, what I would like your guys' help with is to teach your peers in class. So Lucas, you kind of did that on the board once. Jordan, I don't think you've had an opportunity to do it yet, have you?
I have not.
Okay.
No, this will be my first time.
Okay. So Lucas, I think you already have the extra credit, right?
Sure.
So you already earned the extra credit because you did that one on the board. Do you remember?
Yeah, I did. I didn't know that would count for it, though.
Yep. And then, so what you'll get, if you're willing to still help, is you'll just be able to skip this question on the test that I'm going to give you tonight to teach all your peers tomorrow, okay? So you'll just be able to skip it on exam 2. Okay. And Jordan, it'll be your choice. You can either skip the question or get the extra credit. My advice is get the extra credit because it's a percentage of your grade. But it's your call. So, all right. So chapter 5 videos are up. I just posted the second one almost like 30 minutes before we started this meeting. But as you know, we're going to chapter 5 because you guys have been given everything you need now for Appendix B and chapter 4. So that will be tested next week. But I need to pipeline and kind of get us ahead here to chapter 5. So tomorrow in class, I'm going to briefly go over chapter 5, if at all, because the videos are up. And then we're just going to do a lot of class exercise and examples and a quiz, so that you guys and your peers reap the benefit of the in-class time. So chapter 5 is very interesting. Chapter 5 jumps all over the place. Have either of you been able to read it yet?
I've done a brief overview of it.
Okay. Jordan, what were you saying?
I haven't had a chance to read it. Not in the book yet.
And that's fine. I don't bring that up to call you out in this video. I'm curious to try to figure out how to start. So Lucas, you might be a little familiar with, it's mostly on memory, but they kind of use that as their launching point to go over error correction, detection, coherence, a whole bunch of different other algorithms that have something to do with memory, but also just, I think they couldn't find another place to put them, so they put them here. Two of your peers last night took on how to create cache tags, so they'll go over that tomorrow, and I recorded that. So when you guys are helping your peers, I'll give that video to you guys so you guys can see that and you won't miss out on that. And then we also went over mean time to failure, mean time between failure, mean time to repair, and availability. So that's all captured, so you'll get the benefit of that. Just like they're going to get the benefit of this video since they're going to be busy teaching. So with you guys, what I'd like to go over is cache coherence. I'd like one of you guys to do cache coherence, and let me see here, and one of you to do hamming. Jordan, I'd like you to do cache coherence. I'll teach it to you so you can teach it to them. And Lucas, I'd like you to do hamming, if that's okay with you.
Yeah, that's fine.
Okay, so who wants to go first then? And it'll take about 15 minutes each, and then that'll be it.
Go ahead.
Okay, so Jordan, I'm going to pull up cache coherence. So let me pull that up out of the website. Hold on one second. And start telling you about that. I had everything pulled up, but I literally had to restart my computer because the process for audio sound in our first meeting, I don't know why, but well, I know why. I think I killed the process when I was busy because it was taking up too much CPU. But anyways, let me pull it up on the Canvas site here. Oh, you know what? It might still be in my downloads. Okay, I think it's still in my downloads. Let's try this. Yes, awesome. Dependability, hamming, cloud cache coherence. 20. Yes, here it is. Okay, so big picture, here's what cache coherence is. So in this chapter, Jordan, in chapter 5, we go over a whole bunch of stuff like I talked about, but one of them is how do we, with multiple different levels of memory, I mean, you guys know this, like your phone you're using, for example, right now, Jordan, right? You got cache, and then you probably got flash or EEPROM that it's using, and there are two different types of memory, right? and one is less expensive and one is super expensive. So they put the super expensive cache next to the CPU. They put the least expensive furthest away from it, and there's much more of it, right? But the issue is we have to go back and forth between the two, right? And virtually invisible to you as the user. So the user has no idea that there's all sorts of page filing and things going on, like pulling books from the shelf in the library. It tries to keep it transparent to you, so whenever you click on something, it just boom, it's available, right? So there's some fun stuff that goes on, okay? One of these fun protocols that goes on is what's called cache coherence, because many modern processors, like this computer is not even what I consider modern, it's within the last 10 years that I'm using, but it's got 4 cores on it, okay? So now you've got a new issue. You have to keep the memory recent, accessible, and current amongst all 4 CPUs, the cache on all 4 CPUs, and your hard drive or RAM or both. So that's called cache coherence. So you get this interesting situation where one CPU may update memory, let's say it updates it in cache, right? But your other CPUs now have what's called a dirty cache, because their values of that same pointer are outdated, okay? So this is what I want you to go through with your peers in class, is this example, and to talk through it as cache coherence, okay? So here's an example where you have 3 CPUs, all right? CPU A, B, and C, okay? Really original naming here, right? And then you have their cache, okay? Assume this is level 1 for all of them, okay? Because it builds quickly, right? Once you get the cache coherent, then you also have to get RAM coherent, all the same. Coherent's fancy word for all the same, right? Then you have to get hard memory all coherent. So generally the way that works is the processor grabs let's say you're updating an array, right? You do an add I or something, right? It grabs what's in the register, right? Updates the register. The register, then you need to update cache, okay, in level 1, and then level 1 may update level 2 or 3, or it may just update into RAM, and then it needs to update into the hard disk or EEPROM, okay? Because lots of things now are solid-state drives, like your phone, okay? But along the way, it also needs to update all the other CPUs, okay? So in this example, so I kind of restated everything just to, not to insult you, but usually people, learning models, you need to hear it a couple times for it to kind of sink in. So in this model, all I want you to do is go through with them in class. I'm going to give you a blank version of this, so I'll delete this, right? I'll give you the filled out version, and then I want you to talk about what I just talked about with you. Okay, hey, this is what coherence is. It's keeping the memory state the same amongst all memory banks, okay? And then I want you to go through the example step by step, okay? So for example, let's say there's a read done by B, okay? And so now it marks, CPU A marks null and null, right? And CPU B marks that memory as shared, okay? Now C does a write, okay? This is all presuming the same memory address, okay? C does a write, okay? That means it to the same memory, okay? Whatever this array is, let's say it's an int or something, okay? So CPU C marks that cache block state, right, as modified. CPU B now needs to mark it as invalid. CPU A still shows it as null, okay, because it wasn't updated. Okay. Now B does a read.
So it's marked as shared when it does a read.
Right, because it's shared by all 3 of these, so it's going to mark it as I'm sharing this, because it has to go out into memory, right, and fetch it, right? Remember we've talked about this in class a lot. So it does the IF and the decode and the execute, and it says, oh, this is just a load word, right? Loads it into memory, and B is going to mark it shared, okay? Because it's a shared cache between these 3 CPUs, okay? So this is like a, as it says here, cache block state. So it's like a little reference table for these 3 CPUs, okay? Right? And so mark to check, good question. Now, when there's a write, right? Now CPU is going to mark its copy of that as modified, and the copy that CPU B had is now invalid because CPU C now has the most current copy. Right? Do you kind of see where the fun begins to ensue with multiple processors? So we do this to ourselves, right? Because we're like, gotta get faster, gotta decrease that effective CPI. So we've got stages, we've got memory hierarchy. Now we're gonna have multiple CPU cores, and all along the way we pay the price. Right? Now we've got to deal with keeping a current state. Okay, and then B does a write also. So now it's modified, and CPU C's is invalid. Okay. Then B does another read on it. Maybe it just needed it for another register or something. I don't know. And you kind of see where this game goes on. Okay. And I just want you to walk through it with them as an example in class. Okay. All right. So you just talk through each of it. Now I want to show you a better example in the book. I may have you also go over this example. One second. Did you have any questions on that? Sorry, I just jumped off of that really quick.
No, that makes sense.
Okay. All right. Now there's one other example I want you to go over. Between the streaming video and recording, my computer processor and fan are now fully up. All right. Let's see here. Try to find coherence. Just had it up. Parallelism and memory. Parallelism, cache coherence. Here we go. So the book gives another example. That one's okay. I talk about that in the slides. That may be the best we've got for this book. Yeah, that's why I think Dr. Glock made that Word document, because the book doesn't give much. Yeah, I talk about this in the video I posted, but this isn't very helpful, and it just shows 2 CPUs. Yeah, I'll just give you that example to walk through, okay, and how to mark and talk through it, okay? So I'll send this to you right now, all right? Read through this, okay?
Yeah.
And then, and then I need to print it. I'll clean this out. Do you have a printer? Are you willing to print it, or do you want me to print it?
I can print it, yeah. Just how many do you want me to print?
Well, let me think about this now, because if I put you next to a board, then you can just erase it. Otherwise, you'll have to print 5 or 6 of them just to fill them out each time. What would you like to do?
So just one per group then?
Yeah, well,
yeah, I mean, if each group that comes around, they can all fill one out, and I'll just kind of guide them through it, that'd be good. So that's like 5 or 6.
Yeah, so if you could print 6 out, that would work. So, and then 1 filled out copy. So you can just delete these, right? Just, once editing is enabled.
Yeah, I can do all that if you need to.
Okay, so read this and then send it to him, and just talk through just very briefly, because I already introduced it in the video, so it's on you guys and your peers to watch those. I know we're under a time constraint because of what's happened and what I had to do, but the videos are posted, so so don't spend too much time introducing it, or else you're not going to get to go through the exercise, and that's the value of these labs. Okay, any questions on that?
Made sense to me.
Okay, if anyone asks in the book, yes, it does go through it, and if they're like, well, the book example is different, just say the book example is highly simplistic. It's not wrong, it's just really simplistic, so it doesn't show the full impact of, like, 2, 4, 8, like in this case 3 CPUs and what's got to go on. So it's just very simplistic, okay? All right.
Okay.
Cool. Thank you so much. All right, Lucas. Now we're going to do Hamming code. So, Lucas, you seem to really be good at math and enjoy math, based on the few samples I've had in class. All right. Hamming code is definitely a math thing. All right. So, have you worked with Hamming code at all before?
Never.
Okay. Jordan, I'm going to mute you just so that, or if you can mute yourself so that Lucas, I get a better image of Lucas here. And that way Lucas probably will take over. So, maybe not. Doesn't matter. All right. So, I'm sorry. Did you say you said never? You've never worked with Hamming code before?
Yeah, no, I've never worked with it before.
Okay. All All right, again, I'm asking so I can get an idea of where to start. So Hamming code, in the video I talk about, it follows suit when, up until now, as I've talked with you guys today, and I talked on the video, for the majority of it, assumes when we do a hit out to memory, that what's in memory is what comes back to us, and there's no inconsistencies. There's no errors, right? But that's not always the case, because we get interrupts, because memory can go bad, which I introduced in the videos, right? That's becoming less likely. I used to see that a lot, like in the 90s and 80s. But anyways, it happens, and so you need to do a method to deal with both to detect the errors and to correct them, okay? And so how the heck do you detect an error when something was pulled from RAM down to cache, or from hard disk to RAM down to cache, and how do you correct it, right? So Appendix B talked about parity of bits, even or odd parity. Have you worked with parity before?
I haven't.
Okay, this is good. This is actually, you guys both are perfect sample students for this then, for the video and everything, because then others will appreciate your questions and the basis of information that's transferred. So parity is a very simplistic method. The idea behind parity, I'm going to pull up a spreadsheet real quick. Let me know if it's showing on your screen. Is that showing?
Yeah, it is.
Okay, so let's say we have 8 bits, okay? So bit position 1, 2, 3, 4, 5, 6, 7, 8. Okay, so we've got a little byte here, right? Okay, so we've got 8 bits, right? And let's say it's 0, whoops, tab 1, tab 1, tab 0, tab 1, tab 1, tab 1, tab 1. Okay, just making some stuff up, right? So how many ones do you count there? Can you see that?
6.
6. So this would be odd parity, okay? So, or excuse me, as it is, it's even parity. There's an even number of ones, okay? So if we wanted to keep it at even, I'm just making this up, okay? If we wanted to keep it, so we need to add a check bit, it's called. So we're going to add a 9th position, and we're going to add a bit. We're going to say 0, because the sum of all of these equals 0, because it's an even number of bits. So if it shows up on the other end, like this, oops, yeah, right, that would be a problem. I don't know if you saw those 2s in there. Like we have a multi-level voltage system. All right, there we go. So if it shows up on the other end like this, okay, so here's the positions. All right, shows up like that, right? How many ones do we have now?
There's 7.
Right.
So now it's odd.
Right, but the check bit said it was supposed to be even, so we can detect there's an error. Do you see that? So that's error detection. Because the check bit said, hey, the sum was supposed to add up to a big O, and it added up to 1. Right?
So that 9th bit is kind of just acting to make sure, if it's a 0, there should be an even amount of 1s. If it's a 1, there should be an odd amount of 1s.
That's correct. Yep, it's the sum.
Okay, so it's a really basic check.
Yeah, exactly. Very, very, right? Because what if this happens, right? If it starts up here like this, right? Okay, all that good stuff, right? And then it comes across like this. Will the check pass or fail?
It'll pass because it's still even.
It's a bummer, huh? so it didn't work, right? So it detects at most 1 accurately, right? Or it could have 3 errors, right? And still be, and then say it only had 1 error, right? So this is like most basic error detection, okay? This was early models, okay? This is like an introductory, okay? So you get familiar with it, all right? Now, someone came up with what's called Hamming code. Because they said not only do we want to detect 1 or more errors, but we also want to be able to correct them. Okay, so they came up based on distribution, a whole bunch of cool math properties, not that we have time for. I'll explain the code to show you how it works, so you can go through an example with your peers in class. And again, this is kind of interesting that they throw this into memory, but I'm going to reemphasize it, have you guys do this and maybe even test on it, because it's invaluable for other examples in computer science and software. This algorithm is used in other places. So it's very good to be familiar with this, okay? So let me move everything over here on my screen so it's not in the way. So here's a good example that they give, okay? Let's go through it first. Hold on. Which one do I want to do? I'll do the slideshow first, and then I'll do the example. So let me pull up the slideshow. Because first you need to understand. So did you see how I set up extra bits, right, with even and odd parity, right? I set up extra bits just to introduce some sort of check, right? Well, you have to do the same with Hamming code. You have to spread out the data bits, okay? So what you do is you follow these instructions, right? It's right in the beginning here. Hold on. Waiting for it. Did I pass it? Ah, there it is. All right. So similar to what I just showed you on the screen. Oh, that's not going to work. I went to my other monitor. I'll just keep this here. Okay, similar. Can you read this all right? Is that big enough?
Yeah, I can see it.
Okay. So here, our black bits are our data bits. Okay, so we have 8 bits. Okay, so 1, 2, 3, 4, 5, 6, 7, 8. Now we introduce 4 bits for parity, the green bits. And we introduce them specifically in these locations. This is what you do with Hamming code. Is the first position of this new byte word that you create. It's not really a byte anymore because it's 12 bits, but it's a word that you create. The first position becomes a parity, the second position, the fourth, and the 8th position. They're powers of 2. So 2 to the 0th, 2 to the first, 2 to the second, 2 to the third. Okay? All right, that's where you introduce them. Okay? Now, you write these based on, just like we did before, what your data is. All right? So here's where I think the book gives a good example. So I'll go back to the book now. So, for example, here is this parity, or is this? There's 2 really good examples in the book. I try to. Here it is. All right. So here's your data. Okay. 1, 2, 3, 4, 5, 6, 7, 8 bits. Okay, so it's a byte. Okay, in base 2. That's why it's got the little subscript here. Okay. So first thing we do is we spread it out to leave positions for each of these Hamming code correction bits and error detection bits we're going to put in. Do you see that?
Yeah, I do.
Okay. Next, right, we determine what bit is going to be in the first position. Okay. So the first position, we're going to create an even parity. Okay. And we're going to base it on 1, 3, 5, 7, 9, and 11. So we're going to base even parity on this position, this position, this position, this position, this position, and this position. Okay, so right now there's 1, 2, 3, 4 ones.
4.
Right? Yep. Okay. So if we want even parity, what value are we going to put here?
A 0.
0, and that's what they do. Do you see that?
Yeah, I do.
Okay. Now we want to set what's in the next bit position, in position 2. Okay. We want odd parity, okay, this time, and we want it based on these positions. Do you see all these positions listed out? 2, 3, 6, 7, 10, and 11.
3, 6, 7.
And this is all in the book on page 445 or 422, depending on your text. Okay. And so they take these positions, all right? So we want odd parity, right? So looking at these positions, right, 2, 3, 6, 7, 10, and 11, right? Right now, it adds up to odd, or 1, 2, 3, yep. So they set the second position there to 1 because they want odd parity. Okay, so they set it to a 1. Do you see that?
Yeah.
Okay, so second position set to a 1. Okay, it's kind of weird because in each of these examples, the next example down, they show you what they set for the previous. Do you see that? Okay, So now position, so that's position 1, position 2. Now we're looking at position 4, right? And they want to check bits 4, 5, 6, 7, and 12. And that's how Hamming code works, is each position checks a whole bunch of different positions simultaneously, okay? Otherwise, we just have 8 and 8. 8 bytes up, 8 bits up, and 8 bits. Each one checks, but that's still not going to fix the problem, right? So Hamming code, you'll see in a second, really cool the way it does this, right? So now we determine at that position, right? Because we want even parity again, right? We're going to put a 1 there, okay? All right. Do you see that? So they put a 1 at that position.
Yeah.
Okay. Now they check the last position, position 8. Okay. And they determine, right, that they want a 0. All right. So you can check that, but it's these positions right here. So it's summing to even parity. So we put a 0 there. Okay.
So why does it check itself? Like that one checks bit 8, or it checks position 8, but it is position
8. They're all included in themselves. Do you see that? They're each included, right? Because it's
Yeah.
the sum including themselves. So it's the sum including themselves, right? Because it wants to sum to even parity, so it includes itself and puts a 0 there.
Oh, okay.
Yeah, good question, right? So now it sums to even parity. Do you see that?
Yeah.
Because it's a 0, right? If they'd put a 1 there, it would have summed to odd parity, okay? All right, so here's the final word, okay? They call it code word, but whatever. Here's the word, okay? Because they need to do one more thing. After you do all that, we invert bit 10 here, okay? All right? As a demo, let's say, I don't know, your hard disk is failing. I don't know what caused bit 10 to invert, but it inverts, okay? So you do all the work. This is what it sends to cache, but this is what cache gets, okay? So it gets an inversion of the 10th position. Do you see that highlighted there in darken? Okay. So when it checks it at cache, right, it'll go through and do the inverse of what we just did, right? It'll go the other way. So it'll say parity bit 1 is 0, so it is 4, 1, so even parity. So it checks each of the highlighted positions again. It checks 1, 3, 5, 7, 9, and 11, right? For position 1. Do you see that?
Yeah.
And it says, okay, it adds up, it's 4 1s, so it sums to 0, so it's okay. Do you see that? Okay. Parity bit 2, same thing. Checks 2, 3, 6, 7, 10, 11. Out of that, it gets 5 of those positions are 1s, so it's odd parity.
So there's an error.
There's an error, right? Somewhere. We just detected now. This is the detection phase, okay? So immediately you would have like a bit or something, a detect bit, right? Something's wrong with this word we just got, okay? All right? But this is where Hamming code gets really cool. This is where it goes beyond detection. So it checks parity of bit 4, again, by checking the same positions, okay? It finds 2 1s, even parity, it sums to 0, so this group is okay, all right? Now, it checks parity bit 8, right? So it checks 8, 9, 10, 11, 12. There's 3 1s, because remember we intentionally inverted that bit to screw up one of them. And it says there's an error here.
Yeah.
It says, oh, there's an error in this, so it detects. So both bit 2 and bit 8 detected there's an error somewhere, okay?
So does that mean will it go between them and figure out where it should be?
Great question. That was such a lead in. I almost feel like I set you up with that question, right? So here's what happens. Check this out. Parity bits 2 and 10 demonstrate there's an error somewhere. So guess what? When we add position parity group 2 plus 8, we get 10. So bit 10 is wrong. That's how Hamming code works. Is that cool or what? So by adding which two groups that the parity is detected in, you can find the position. And now you can just invert it and correct where you had the error. And now you have valid code.
Can you scroll up just a little bit so I can see the position 1, which ones it checks?
Oh, sure. Right here. So position 1 checks 3, 5, 7, and 9, right? So 10's not included in there. Do you see that? Position
And those are all odd numbers because you could add a 1 to it. So that would make it odd.
Yeah, you can think of it that way. but these are the positions have to overlap, right, for the math to work. And I'm not going to go into all the details. So you're already going into it. You're very intelligent because you're already like, wait, okay, so if there's odd here, and even that's right. So he did all this for us, right? So if you want, you can look this up afterwards. I'm not. If I go into this, I'm concerned I'd lose a lot of people. But big picture, right? There's overlapping parity, right? So there's redundancy here, right, between multiple groups, right? And it provides us error detection and error correction. Okay. Did you understand the example that we walked through?
Yeah, I did.
Okay. So again, first you have.
Sorry, I kind of one more question about like the math with it all. So position 11 is the only one across 3 of them, and that's just because we have to check 8, 2, and 1 to get to 11. That's the only way to get to 11. Because that's the only one that's through all 3, through 3 of them.
That your math is correct.
Okay.
Yeah, there's some cool, really cool stuff that I mean this is kind of his magnum opus, right? This is why it's called Hamming code. He did a really good job. Hamming code is used over the air. It's used in all sorts of applications because of its usefulness. Because we can think. I mean, big picture. Think about it. We're sending 8 bits. We only introduced 4 more bits, and we can get up to, I think it's 2 detections and 1 correction. That's a really good payoff for only adding half more bits. Do you see what I'm saying? And it detects it detects errors, within itself. So that Hamming code is extremely efficient. Okay, there's some things called Viterbi and some other stuff, but that's way outside the scope of this course. So Hamming though is a good way to introduce students and to teach students how error detection and correction can work, because it's kind of a code game. Okay, with numbers. Okay, so I'd like you to walk through this example with them, all right? And you can just really have your book open and explain it and walk them through it, okay? So that they get comfortable and familiar with this, because I think there'll probably be an exam question on this, and I'll invert a bit, and I'm going to have them find, just really easy. I mean, you can just check the parity of the groups and find which bit it was, right? So, so please make sure you go through this example in class, okay?
Okay.
All right.
And that's page. What page is that again?
It's 422 or 445. The way my PDF displays it is as 445 out of 793. So maybe that's after all the formatter, but it also shows 422 as a reference. Let me see what it says on the bottom of it, if it's paginated. Hold on one second. Here it gets into more of what you were asking about right here. Okay, in those pages. Okay. But yeah, my pages aren't. Oh yeah, it's 422. Do you see that? According to the way the book is paginated, do you see this up in the corner? Yeah. So it's 422. So 445 must be just in the PDF. Okay, so that puts us exactly at 4 o'clock, about 15 minutes each person. We got started a little late. Thanks, Jordan, for being patient and struggling through and getting your stuff working. So that makes this more useful. You can re-enable your audio there, Jordan, if you're still silent. Do you guys have any final questions before I end this and stop the video?
Yeah, I think I've got it. So.
Okay, Jordan, did you understand what I explained to Lucas there on Hamming code?
I'm sorry, what?
Did you understand on Hamming code what I went through the example with Lucas?
Yes.
Awesome. Because, that's why I like to do you guys together, and then there's another video available, because that way when you guys are teaching, you're not going to miss out on seeing this, right? So I'll send you guys the links here later tonight after the last group goes, so all of you have a little mini video of what I went over with the others, so you won't miss it, okay? So you'll get the value of that, okay? And actually, you'll probably get the best out of any of the students. And you guys, if you have any other questions, let me know, okay, right away. All right?
Okay.